Next up is Gleb Naumenko, also from Chaincode Labs, and he'll be giving a review survey of P2P and broadcast technologies with reference to Bitcoin. Thanks, Gleb.
Hi. I work at Chaincode on peer-to-peer protocols. My research is focused on Bitcoin, but the ideas I have are applicable to other systems as well. For some reason, they're not that interested in this research, and that probably tells you something about them. But yeah, let's see what's going on. So this talk is for those who understand Bitcoin is a high level. Bitcoin is a cryptocurrency. It's peer-to-peer and all that, probably you know, and want to contribute to peer-to-peer research directly. So want to help us to protect the network from attacks, to analyze it, to see how to optimize it. But also, this talk would be interested to those who want to see peer-to-peer network in the more interdisciplinary research, and I'll try to talk to that at the end of my talk. Bitcoin exists to exchange transactions. Bitcoin is a financial system, and we have blocks and we have like all the fancy stuff, but at the end of the day, you just want to send money and tell other parties in the network that transaction went from party A to party B. And today, Bitcoin runs on the 60 machines in the world, 60,000. 60,000 people run software at their homes or in a cloud to exchange transactions with each other. But is this even true, like about 60,000 nodes? Most of the researchers look at this website, localhost, or run it by themselves and see that it says 60,000. But it's a closed source crawler, so nobody knows. Luke knows, and some of the Bitcoin developer knows how it works, but it is closed source for a reason, because if we make it open, then it will be easier to trick. So this model was chosen. And there was a paper in 2014, I believe, that said that it's actually a bit wrong, and we have less than 60,000 nodes. So this topic needs more research, and we don't understand the network quite well. The network is not supposed to be totally public, because if the network is public, it's easier to attack. There is an ongoing discussion whether it should be public or not, but the current state is this. Most of the researchers guess it's 60,000, but more research should be done here. OK, so there are 4 properties of the peer-to-peer network of Bitcoin, I believe. It's security, how to make attacks on the network more expensive and harder. For example, how to make it cost millions of dollars to shut down the network, to stop transactions to propagate. At the early days of Bitcoin, it would probably take $100 to stop the network, because there were like DOS issues Ethan talked, and now as the system evolves, it's much more expensive, and we're constantly working to make it more and more expensive. Privacy, how to increase the cost of de-anonymizing transactions, for example, of linking a transaction to an IP address, because Bitcoin doesn't guarantee privacy, but we take a lot of effort to make de-anonymization as expensive as possible. Latency, how to make it so that your transaction propagates across the network as fast as possible. We went from seconds to milliseconds now, and transactions propagate across the network very fast. And the last is resource consumption. Part of Bitcoin's philosophy is to allow all the users who want to verify the system from scratch to be able to do this. For that, we need to reduce the bandwidth needed to run a node, so that you don't have to pay a lot of money for internet you run your node on, or to not require to run an expensive computer to verify everything in Bitcoin. And yeah, let's see what was the research on peer-to-peer security first. There are 2 major attack vectors I consider: targeted eclipse attack and network split. Targeted eclipse attack is when you choose a victim node, and you make it so every node connects to 8 other nodes by default. So you want all those 8 nodes your victim connects to be malicious. For example, be nodes controlled by yourself. If you eclipse a node in that way, then you can trick it. If it's a merchant, you can make them think that you paid them, but actually didn't pay. And that way you can get goods for free. And a network split is split in the network graph. So those 60,000 nodes in two segments which don't talk to each other. And yeah, let's see. Eclipse attack allows to feed a node their own chain. So you have a victim, and you, instead of showing it the valid Bitcoin blockchain, you show it the fake chain you produced. And in that way, you can try to double spend it, the way I explained with merchants. You can spy. You can see which transactions were originated at that node. You can even propagate it to the network, but you will learn who they transact with, and then you can go after them. Or make mining less efficient, that if you're a miner, you want to make other miners to be less efficient because you compete with them. And if you do this to their node, they're screwed. This work was thoroughly explored in the Bitcoin context by Ethan and his co-authors 5 years ago or so. Yeah, so to understand why it makes mining less efficient, let's understand what's a stale block rate. So miners can currently work to produce blocks, and if they produce two blocks at the same time, at the same height, only one can be part of the main chain. And other block, even though it is valid and somebody spent a lot of hash power to produce it, will never become part of the main chain. And that's essentially wasted work. It is dangerous because wasted work, that work they contribute to, would otherwise become a part of the security of the entire chain. Because if you can redirect that spent hash power to the actual chain, then the network will be more secure. And this heavily depends on the on the latency, and if miner is eclipsed, then it becomes more often. Yeah, so to launch this attack, you need a big long-living Sybil botnet, so a network of machines you control, and you use them to eclipse somebody. So Bitcoin network is 60,000 nodes. If 40,000 of them are malicious, then it's very likely that a lot of nodes in the network will be eclipsed. Or actually what Ethan showed, he showed a bug in the Bitcoin source code which allowed you to eclipse a node even without a huge botnet. But that's already patched, and that's not the case anymore. This is a recent attack. It's very similar to Eclipse attack. It was published this year, except to run it, you need to have a large corrupted ASN. ASN is a sort of network provider abstraction. So, for example, 25% of the nodes today in Bitcoin network run on Amazon, DigitalOcean, and some third German provider I don't remember of. So that's bad, because if those three are collaborate and become malicious, then they can do whatever they want with the network. So decentralization in that sense is important, and there are ongoing efforts to make diversity of connections your node creates all the time. OK, let's look at the research on the privacy. There are 3 types of attacks. The anonymization of transactions, when an attacker tries to link a particular transaction to IP address it originated from. Because by IP address, you can see where a person is located and go to their home and rob them, or I don't know. Then topology inference, when an attacker tries to see what the topology of that 60,000 of network of nodes, because if they see it, they can attack it easier. And identifying miners exchangers, because if they know which nodes belong to miners, then they can spy on them, they can attack them, eclipse, and all that stuff I talked before. Dandelion is a cool research project which changes the way transactions propagate across the network. So normally, you receive a transaction and you send it, you validate it, and you send it to all 8 peers you are connected to. And then all those 8 peers do the same thing and relay it to everybody. Because of this protocol, it's trivial to find where is the origin of a transaction, because obviously the one who sent it to you first is the source, because you just assume that they knew it earlier than other nodes. So Dandelion obscures the way transaction is relayed across the network, and they have this anonymity phase where you just send through one link, and then the next node also sends it through one link, and after, on average, 10 hops, it starts to spread across the whole network. So that's why it's harder for an attacker to distinguish first node in this chain from the second, and so on. Unfortunately, it's hard to build a robust and efficient implementation of Dandelion in Bitcoin due to the policies we have. It's an ongoing struggle. I hope it resolves at some point. But if you're really interested in this, just take a look at the online discussion, and perhaps you'll find a way to make it happen. Basically, the problem is it's easy to create transactions which will propagate through the stem phase, the first anonymity phase, but never relate at the second fluff phase. That's why you can feed nodes in the network a lot of transactions which never propagate and just exhaust their memory. CoinScope is another attack on anonymity of the network, and it allows to learn the topology of the network by using various policies. So for example, by the way we handle double spend transactions. So if there are two invalid transactions, you can trick the nodes to propagate them in a different way and learn the topology that way. And one of the results of this work is the communities in the public Bitcoin network. So most of the research assume that Bitcoin network is a random graph where everybody, like all the connections are distributed and they're uniform and there is no such communities. But in practice, they used CoinScope against testnet, Bitcoin test network, and found this. And yeah, this is really interesting. And we don't want these techniques to be possible in the mainnet, because if you can learn the topology, it's easier to attack it. So if you learn this, you can find the bridges between those communities and attack them. And by that, you can split the network. This is not desirable. Researching the peer-to-peer relay latency. One idea introduced by Matt Coralla a couple years ago is a compact blocks protocol. It makes blocks propagate across the network much faster than it used to. It used to take several seconds and more to propagate blocks in Bitcoin network across the network. I previously explained why it is bad, because if blocks are propagating slow, then miners are much often work on the same height. So the number of produced blocks at the same height is higher, and security loses. And yeah, so this was important to mitigate that. And yeah, it also reduces the bandwidth every node needs to run Bitcoin, and this is also important for that accessibility property I explained. Fiber is also by Matt. It's a separate parallel relay network among miners where they exchange blocks super fast for the same goals as I explained before, to reduce orphan rate. We shouldn't assume fiber is always available. So even though fiber is great and it works, we don't want to adjust protocol assuming that it always works, because it's a centralized server. If MED is corrupted or if it is under attack, network should still be robust. And so one of the arguments why Bitcoin block size is 1 megabyte is because we don't want to increase the orphan rate. Fiber helped to reduce the orphan rate significantly, but we still cannot make that assumption in the core protocol. Another recent alternative idea is Catcast. So somebody suggested to use Kademlia relay to relay blocks across the network. It's a computer science protocol which was originally used to find content in distributed systems. So you can look at the key of the content and try to find which node store it. Like, for example, like in BitTorrent. It is not used in BitTorrent, but that's an example. And somebody suggested that we should use this to relay blocks. This protocol is also used in Ethereum for their peer-to-peer network. Ethan showed that it is not secure, and they took some of the countermeasures, not all of them, but Yeah, so it's really interesting. People keep suggesting using Kademlia and Bitcoin. This works as, okay, so there are problems with Kademlia, but we can solve them by asking nodes to run proof-of-work puzzles for Sybil protection. That's not an acceptable solution at all, because you cannot. This just makes the network permissioned, and that contradicts the goals of Bitcoin. And if you want your protocol to be feasible, then you don't want this assumption that you can ask everybody to run proof-of-work puzzles just to participate in the network. Yeah, and finally about optimization, I've just mentioned my work. We found a way to change the way transactions are relayed in the network. So now your minimal node spends 30 gig a month to participate in the network. And we found a way to reduce it to 16 gig a month. And secondly, your node currently connects to 8 nodes in the network, but if you want to be more secure, you probably want to increase that to 16 if you run a big exchanger. So if you connect to 16 people, you would spend 60 gig of bandwidth per month, so twice as much. And with this protocol, the cost remained the same. So it was 16, and it will become 17 or so. And it also accidentally makes privacy and block relay slightly better and faster. So I also have a list of helpful like low-level ideas we have in Bitcoin Core, which will help for further research. There is an understanding now that block relay and transaction relay have solve two different problems, and it has different properties. Block relay should be as fast as possible, because I explained why, because of orphan rate and security of the network. We don't really care how much bandwidth we spend on block relay, because blocks happen every 10 minutes, and it's fine to spend a couple more megabytes on it. We also don't care much about anonymity of block relay, because we can just assume that miners can run multiple nodes and be secure against certain attacks. While for transaction relay, you can sacrifice latency. You can take a couple more seconds to relay transaction across the network. Right now, it takes 4. In my protocol, it takes 6 seconds, which I believe is not a big concern. So yeah, this is one hint. So future protocol developers, if you want to change peer-to-peer, I believe you should take this into consideration. Package relay is an idea where you, if you have 2 transactions which depends one on each other, you want to relay them together. This is helpful in various contexts, and right now it's not handled by any good solution, but there is ongoing discussion about it, and this also should be taken into account. Nodes are updating slowly. So right now we are around 0.19 version of Bitcoin Core, but a lot of people, I have friends who still run 0.17. So this has advantages and disadvantages. And advantages, obviously, we are improving the software. That's why we want people to update as often as possible, because they can benefit from optimizations. But also, if you accidentally introduce a bug, if everybody updates that, everybody is screwed. If all the nodes are there, they can help to detect a bug or to keep the system alive. And yeah, but this should be taken into consideration when you think about deployment of your protocol. Topology is not random. So even though a lot of researchers assume that the Bitcoin network is a random graph, in practice it's not, because if you run a node from 2011, you have a lot of inbound connections. You probably exhausted your number of inbound slots, because there was a high probability that in early days people were connecting to you and kept connecting to you. So yeah, so this should be taken into account. And connections are still not encrypted. So two Bitcoin nodes talking to each other talk in plain text, and internet provider can see what they're saying. There is an ongoing work in improving then finally encrypting connections. I hope this happens this year or next year, but it's still not, and it's a room for research. And there is a lot of room for scientific contributions, I believe. So I just showed the examples of the projects are going on, but you can build your own, because it's like it's pretty early days, and peer-to-peer research needs more attention. Yeah. It seems like I have a bit of time. I have a couple bonus slides. So I'm interested in this problem, game theory and peer-to-peer. Miners obviously want to increase their revenue. That's what we should think of them. Miners are incentivized to get as much money as possible. And attacking other miners sometimes increase their revenue. So if you make other miners less efficient, then you can make more money by yourself. So I'm interested in how feasible it is to one miners attacking each other on the peer-to-peer layer. So for example, if you can shut down a node of other miners, you can stop them producing blocks, and you can increase your revenue. But if this attack is too expensive, then you probably just spend money on your ASICs. And would they do it even if the price goes down? So if this attack is detected, people can give up on Bitcoin and switch their investment somewhere else. But how would the parties act in this way? OK, so if somebody is interested in this, please talk to me. OK, I'm done.